Say you drive a Chevy. Say you drive a Ford. You say you drive around the town till you just get bored. And then you change your mind for something else to do. And your heart gets bored with your mind and it changes you. Well, it's a doggone shame. And it's an awful mess. I wish you love. I wish you happiness. I wish you love. I wish you happiness. I guess I wish you all the best.
Hello. I'm audible, right? Good. I'm Joe Rudnick, a one-time member of the Department of Physics and Astronomy, and the last 10 years of that time, I was also the Dean of the Division of Physical Sciences. So I played some role in the creation of this wonderful institute. Is Manny here? Manny here? Not right now. No, that's fine. That's fine. And I was going to just waste not too much of your time just recounting how this whole thing started. There's one thing that I discovered if you want to be a success as an administrator, you need to develop the facility, you need to develop the ability to recognize a good idea when you see one. There's that, and there's the fact that when you're an administrator, at least at the level I was, every problem, every issue, every decision basically boils down to money. Yes, I saw somebody almost cough up his. Yes, it's true. It is true. I mean, it's really, it always comes down to money. So if you can recognize a good idea when you see it, and if you have money, wonderful things can happen. It's the money part that generally gives deans ulcers. But it turns out that there was a time when Mani and Zvi and I happened to be having dinner together at the Bel Air Hotel, that money was actually looking good for me. And it's because a faculty member in the UCLA Department of Chemistry and Biochemistry had successfully synthesized a cancer drug that is extraordinarily effective against otherwise intractable prostate cancer. And in fact, it became what is known as a blockbuster. And because of that, UCLA was able to sell the royalty stream to a group of investors for about $1.2 billion. Good fraction of that went to Mike and the other people who worked on it very appropriately. But some of it went to the Division of Physical Sciences. And even a small fraction of $1.2 billion is a lot of money. So when we were having dinner and I was feeling very particularly expansive, it hadn't yet come, but it was going to come. And actually most of it has come to my successor. I proposed to Mani that he and I go in together at $1 million apiece for a graduate fellowship. And Mani, who I think really knows a good idea when he sees it, agreed immediately. So we toasted this wonderful development. And then the next day, Mani spent some time with Brooke Sanders, the executive director for development in the Division of Physical Sciences. And They emerged from that meeting with a plan for an institute for theoretical physics based on Mani's generosity. And I would like to say now that the rest is history, which is almost true, except I have to qualify a remark that David Gross made at the beginning of his talk. He contrasted the situation in India with the situation here in our neck of the woods by saying India is difficult and here it's not so. That's not entirely true. And I'll maybe if later I will go into this, but in part it's because there's an inherent faculty culture of conservatism. There is the old joke that every faculty member knows or ought to know, which is the answer to the question, how many faculty members does it take to screw in a light bulb? Of course, the answer is change. And that, well, anyway, thanks to Zvi's leadership and to Mani's generosity, vision, and deep appreciation for the importance of physical science, theoretical physics, and for the day-to-day challenges of those who pursue that discipline, the Institute is now a thriving enterprise, and I think one of which we can be proud and will be increasingly proud. So with that out of the way, I'm going to introduce our first speaker, Professor Eva Silverstein. She's a theoretical physicist, cosmologist, and string theorist who's especially well known for multiple contributions to string theory and for important contributions to cosmology. She's a professor of physics at Stanford University and a director of the Modern Inflationary Cosmology Collaboration with an Simons Foundation Origins of the Universe Initiative. She is, of course, multiply recognized. Among the honors she's received, well, honors plus money has been a MacArthur Fellowship. And so now, without further ado, Professor Silverstein.
Thank you very much. It's great to be here, and I want to add my voice congratulating the Institute for a brilliant 5 years and with hopes for many, many more. And happy birthday to Mani, who I had the distinct pleasure of discussing physics with last night. So my talk will cover areas of theoretical cosmology. And what I'm going to aim to get across is both the breadth of the field. I mean, after all, in some sense, it's everything, cosmology, the history of the universe. And it's a field which is grounded by spectacular observations. I don't know if this works. It's grounded by spectacular observations on the one hand, which we'll cover in part one, which I apologize in advance, will go a little fast because I also want to get to the other end of the subject, which is the sort of more, if you like, thought experimental side, conceptual questions in cosmology that were touched on a little bit this morning, and explain a little bit of progress toward understanding the nature of microstates in that context. And then if time permits, which it almost certainly usually does not, but we'll list it here anyway, the scope is even extending these days to potential spin-offs for more practical matters, cosmological evolution models in the context of optimization in artificial intelligence. So if I get there, I'll try and explain this scope, but with more of an emphasis on what I'm calling part two here. So first and foremost, though, happy birthday again to Mani and to his institute. It's a phenomenal undertaking that we all benefit from around the world. So it's a fact about our theory of gravity, general relativity, that it predicts a multitude of space-time backgrounds. The fact that string theory predicts many solutions is a generalization of that basic fact about general relativity. And one of the striking aspects of these backgrounds that it predicts are horizons, where observers cannot see behind due to the finite speed of light. So we heard this morning about black hole horizons and some of the progress there. I'm going to focus on cosmological horizons, which pertain in the real world case that involves exponential expansion or accelerated expansion of the universe. So here the metric tensor, homogeneous approximation is very simple, describing essentially exponential expansion of the spatial dimensions of the universe as a function of time t. We heard this morning, so here at the top is kind of the intuitive picture of that the space is stretching out exponentially. And as a result, again, of the finite speed of light, if two observers start out nearby, they end up unable to communicate. In terms of the kind of Penrose diagram that we heard about for black holes this morning, the Penrose diagram, for which light goes at 45 degrees angles, that Penrose diagram is as simple as it can be. For de Sitter spacetime, it's just a square. And the spacetime itself is highly symmetric. So there are certain aspects of the spacetime that are truly simple. And in asking some of the deeper questions, we'll actually find some benefit from that simplicity in a way that we'll see shortly. Okay, but first let me do part one. This is a fact about nature, that the expansion of the universe is accelerating now. And this was a discovery about 20 years ago that I must say surprised theorists for no particularly good reason. There was a kind of prejudice against it, but there it is. That's in the late universe, taking over now. Also, there is very strong evidence for a theory of origin of structure that is based on accelerated expansion having happened in what we often call the very early universe, though who knows how far back in time the universe goes. But up to about 14 billion years ago, we actually have some observational handles on that. And the facts that we observe through things like the microwave background radiation fit beautifully with a scenario called inflationary cosmology, in which the expansion of the universe is driven by a slowly changing potential energy at early times, which eventually exits from that phase, giving more modest expansion that we see in the kind of intermediate periods in the universe. And just saying that there's some degree of freedom, some scalar field, let's call it phi, whose potential energy takes that form, implies that its quantum fluctuations appear. There's the Heisenberg uncertainty principle, and there are these irreducible quantum fluctuations. In the context of the acceleration of the universe, those fluctuations exponentially spread out, and they survive. They do what we call freeze out, and again, their amplitude is fixed by the uncertainty principle. And after the exit from inflation, one can evolve forward the equations of gravity combined with the other forces of nature and figure out what the observational signature of this should be. And trying to get this to advance. Sorry, not sure why it won't advance. Yes, exit. Speaking of freeze out. Yeah, it's on my laptop. I'm not able to escape or do anything. Oh, there we go. Okay. Did it now work? Svi, I just needed you to do that. I'm from Silicon Valley, but I can barely use a computer. Okay, so these quantum mechanical fluctuations, again, they must exist. They're predictive, and long story short, on the right, and it is a long and beautiful story, the observations that we make that I wanted to say in the intermediate slide here in the microwave background radiation that streams to us from when atoms formed, and in the pattern of large-scale structure in the universe, the statistics of those observations fit very precisely with the origin of the structure as having come from these essential, the variance of the fields in the early universe, the inflaton field, and all these facts are fit with just a Gaussian random field as the initial condition motivated by that paradigm. In a sense, this is an observation of the same phenomenon that leads to the Hawking radiation in the case of black holes, but here they're empirically observed. Okay, so that is really a beautiful development in the past several decades. So on the one hand, this subject is very, very grounded by those sorts of observations, combined with a simple but conceptually very important theory. On the other hand, it connects to questions that are so big that, as David stressed, we're at a loss. So this slide is an attempt to kind of depict all of that at once. So here we are observing within the light cone, our past light cone, and we get clues from the microwave background, from the large scale structure that fits with inflation, and from which we can glean even more information if we can get a handle on the nonlinearities of the large scale structure in the universe. And this is a very active area of important research that's led by folks like Santore Zaldarriaga, Seljak Wandel, et cetera, aiming to extract even more information about the statistics of these early universe fields. So that's, all very sharp and empirical, with a beautiful harmony between theory and experiment. On the other hand, it connects to questions that we can't help asking about what's going on beyond that, both beyond the horizon, at the level of the horizon. What about the microstates of the de Sitter horizon, this cosmological horizon? And well, that's what we'll get to below in the talk. What about higher moments of the primordial distribution that generated these fluctuations, for whose effects we've only really understood at the Gaussian level so far? So we need a non-perturbative understanding of the quantum fields in the early universe and the best way to extract their signatures in the data. The subject is actually sensitive in a very precise sense to quantum gravity, believe it or not, although we can describe all of this as in terms of quantum fields. To understand inflation properly in our standard framework for parameterizing our ignorance of higher energy physics requires controlling effects that come from quantum gravity that are, in the sense of the Lagrangian, are suppressed by the Planck mass scale and yet matter for inflation. And so that's been a big industry leading to development of inflationary mechanisms in string theory that in some cases have rather distinctive and testable signatures of their own. And that's an ongoing enterprise. Beyond that, as David already said, the picture that we do get out of quantum gravity, out of string theory, is that this accelerated expansion exists, but that it's only metastable. So it eventually decays into a more complicated future. And as Juan stressed, there's, in any generic evolution backwards in time, you hit singularities that need to be resolved, maybe topology changes, dimensionality changes, and so on. So we get into these really, almost ridiculous questions, starting from this very grounded situation we're in, where we can infer the success of the basic phenomenon of accelerated expansion of the universe. So that's, I'm trying to give a sense of what a wonderful subject it is in that regard. There's serious questions for theorists to still grapple with, while at the same time, the whole thing really is grounded empirically. And there's more to do at that interface. Okay, so I already mentioned this. Let me go quickly through this. I already said this in words, so I'll just flash the equations that go with it. Inflationary physics is sensitive to Planck suppressed corrections in the Hamiltonian of the theory. And in string theory, the way that inflation comes out involves involves mechanisms that are not quite as naive as you might guess from the bottom up, with, say, a parabolic potential. Instead, it gets flattened out. And axion mechanisms for inflation give a particular sort of set of predictions that are in the process of being tested by data. And there's a whole zoology of these going on. The perturbations, just filling in a few more of the equations, are both scalar and tensor. The primordial gravitational waves are of special interest, while the scalars have been seen at the Gaussian level, which is only part of the probability distribution that we get from their full wave function that could involve effects of additional fields and interactions that would show up in higher moments and other features of the distribution. So at the Gaussian level, there's a lot of progress empirically. The constraints on these models in terms of the way that the spectrum depends on scale and the amplitude of these gravitational waves has made dramatic progress. It's getting to where it's going to test very, very different classes of inflationary models, and that's exciting. There's a lot of information left in the Gaussian part of it because the results that I flashed earlier assume a very featureless power spectrum, whereas all sorts of kinds of physics of additional fields that might have been in the universe and their interactions could even imprint signatures on this quantity. And so there's ongoing work to understand both the Gaussian and non-Gaussian statistics of the primordial perturbations. So let me just kind of leave it at that. There's a lot of work on this subject. I've kind of given a laundry list of various approaches and results related to it here. That includes beautiful calculations of perturbative correlation functions, as well as calculations of more non-perturbative aspects, shape of the tail of the distribution and such things. And there's a lot of room for extracting more information from these studies. As I said, I want to get to the other part of the discussion, so I'll just summarize. The status is very rich in interesting theory and phenomenology. Here's a kind of summary of the empirical side, where the microwave background measurements are proceeding to get more modes and attack the problem of the primordial gravitational waves with foregrounds. And at large scale, in the sense of the large scale structure, the challenge is, of course, that is very nonlinear. It involves nonlinear physics that needs to be separated out from any kind of primordial signal. And so there are very interesting approaches to that that have made some progress. Here's one from the group of Senatori and company giving a measure or a constraint on one of the most important and difficult forms of non-Gaussianity, which is a certain shape of a three-point function called equilateral, where it's not quite at the level of state-of-the-art CMB, but it's competitive with WMAP now, with data from the same kind of time as WMAP in large-scale structure. And as Leonardo says in this slide, the future may be bright because there are all sorts of projects aimed at gathering quite a bit more data. Okay, so here's a summary of part one. And there really is a wonderful challenge on this side of the subject. But now let me move on to the next topic, which is kind of on the other end, and perhaps more in tune with what we heard about this morning, which is to try and understand the statistical mechanics of the accelerated universe. So here again is a picture of the horizon and at various levels of abstraction. Globally, you can think of de Sitter space as a exponentially contracting and then expanding global space-time. Again, here's the Penrose diagram describing that in a more succinct way. So as we heard this morning, semi-classically, researchers in the 80s came to an intriguing connection between the geometry and classical dynamics of horizons, black hole horizons, but also they made forays into the cosmological case, in which there was a tentative association of entropy with area, with the entropy, including the quantum fields, as we heard this morning from Juan. And again, with the area of the horizon being related to an entropy, and there are different versions of that, but the most, perhaps conceptually most simple, is to think in a microcanonical ensemble where the entropy is the log of the number of states at a given energy. And does that work? Well, for certain black holes, it was shown to work. So these were famous calculations in which one took the famous D-branes of Polchinski in string theory, calculated the state count at weak coupling. So in a very easy to control calculation, when the interaction strength of the various constituents here are weak. And then one uses a kind of symmetry that guarantees that that state count doesn't change as you go from weak coupling to strong coupling. And at the same time, you can show that that interpolation of strong coupling takes this D-brain system with strings on it and so on, and turns it into a proper black hole with a horizon. Now, what's going to happen in the cosmological case, the recent progress there, in effect, or in essence, replaces this control method, the supersymmetry, to control the count of states as you deform the theory from something you know to something you didn't a priori know. Replace the supersymmetry with what's called an integrable deformation. So a kind of control of the count of states that obtains in a very different way from supersymmetry that has been pioneered by Zamolodchikov and other researchers in the field over many years. And there's been a wonderful confluence of threads in theoretical physics that have led to this type of result. So that's what I'm going to try to explain. So happily, I can continue to build off of what was said this morning. So there's this beautiful ADS-CFT correspondence of Juan and others, which applies a negative cosmological constant. It has so the Penrose diagram for that is this can, and at infinity, so the boundary of this can, sorry, I keep forgetting this doesn't work. The boundary of this can is actually at infinite distance, and the fields are just pinned there, and you get a non-gravitational dual description. The way that works, in full detail is not known, but there are some nice qualitative aspects to it that I want to build from, one of which is that in this correspondence, the boundary corresponds to very local short distance physics. And as you go more toward the middle of the bulk, you get more low energy physics. And the description from the CFT point of view is, when you think of it in terms of the local operators, becomes more and more complicated as you go toward the middle. But in any case, that's the dictionary. There's a relationship to entanglement entropy, which we heard about this morning. But let me move to the method that I want to explain today, which again has to do with a kind of deformation, not a supersymmetric controlled deformation, but what's called an integrable deformation. So to get there, let me start from what we just said. There's this ADS-CFT duality. We're interested in getting to the case of cosmology, which, as I mentioned, has this hyperboloid with, if you think about that global space, it has no boundary, certainly no boundary at infinity. Even if we look at a finite patch of it, it's not that there's a boundary off at infinity. So people have thought that, therefore, one has to do something very different than ADS-CFT for cosmology. But instead, we're finding that one can get there. One can start from ADS-CFT, make a deformation of the theory, which eventually gets us to the finite patches of space that pertain in cosmology. So I want to explain this approach, what's included in it, what the results are that match, what's included and what's not captured yet. Okay, so let me start from the idea. It's weird because on my screen I see a bunch of Zoom things that are in the way. But in any case, okay, we have this problem that ADS goes off to infinity, whereas cosmology is finite. So the first thing you might try to do is at least get a finite patch of ADS and formulate that. So there has been a direction in quantum field theory in which Zamolodchikov and others have understood how to deform quantum field theories in a way where you can still calculate the energy spectrum, and in which the deformation affects the high energy physics. So if we want to, say, get a finite patch of ADS by bringing in the boundary, well, we have to do something to the high energy physics. So these two directions at least qualitatively match, and in fact, they perfectly match. So let me, again, get to the start from the general idea, and then I'll get into more of the details. So basically, we want to deform the CFT so that the high energy part is missing to get, instead of the whole thing, get rid of that asymptotic boundary. And by using the results of these solvable integrable deformations of quantum field theory that I'll spell out more shortly, it was shown first by McGuff, Mazet, and Berlinda that the calculable energy spectrum of that deformation matches precisely with what you would get if you bring in the boundary of ADS. So if you start from some CFT that has an ADS dual, then you can deform it both in the boundary description and the gravity description, and the two match perfectly at the level of the energy spectrum. And I want to highlight here that Per Krause, who is one of the leading figures in this field and a UCLA star professor here, has been leading the charge in various ways in this correspondence with many very brilliant young collaborators. So I feel a little bit like, bringing whatever it's called, bringing coals to Newcastle, or maybe solar panels to LA is better said. But we've, enjoyed discussions, and I'm excited to learn more from their group, where they have really made this correspondence much more explicit. So we start from that, and what we'll see is that there's a kind of two-part deformation in which we can follow this count of states and the energies, which relates directly to the geometry, follow both of them in a controlled way, and go from ADS CFT, bringing in the boundary, going to a horizon, switching the deformation to a still solvable one, for which, as we move further in this solvable space, we build up the energy spectrum and the count of states for a patch of de Sitter spacetime, the accelerating universe. So that was the subject of this paper with a wonderful crew of younger researchers and based on earlier works, as these things always are. So let me go back to the beginning again. As we've heard now a number of times, including earlier in this talk, there are these gravitational calculations that suggest a thermodynamic interpretation of horizons, both in the black hole case and also in the de Sitter case, which has been more mysterious. And I'm going to drop down to 3 space-time dimensions. This is a dimensionality in which the problem still exists, and we will have the tools to address it. There, as before, the gravitational prediction would be that the entropy, the log of the number of states associated with the horizon, is the area in units of g Newton with a precise 1/4 factor. And then there are corrections of the sort that Juan already alluded to. And in this context, they were calculated by Niños, giving a particular logarithmic correction here. And there's a whole series of such corrections. Okay, so the upshot of this paper is that at the level, the leading order, these results emerge from a solvable deformation of a conformal field theory. So we start from a conformal field theory that has an ADS dual for which we know the whole spectrum, or we know enough about it to count the states associated with black holes in ADS space-time. And we can deform that theory in a way that remains solvable. So we can follow the energy spectrum, including the count of states precisely. This deformation is known as the TT bar deformation, augmented with an equally solvable addition that we call lambda 2. And by solving that theory, we morph our boundary theory from the ADS CFT one into a theory which reproduces the energy spectrum and the state count expected for the observer patch of de Sitter, the one with this bounded by our horizon. So it captures those things, and it does so precisely. It gets those answers on the nose, and these are functional matches of the duality. On the other hand, we know what it doesn't capture, and it does not capture other kind of model-dependent details of bulk physics that are sub-leading in the large N sense that David Gross actually introduced in the context of QCD. Okay, so what am I talking about when I talk about deformation? So think about the action of the theory or the log of the partition function. We, following Zamolodchikov, consider a deformation of the theory, which we can describe as a differential equation, d by d lambda, where lambda is the parameter along the deformation. And so at each step in the deformation, we add a particular quadratic combination of stress energy tensor components. And also, we are free to add a constant at every step. So what we will do is first start with the seed CFT. We will add the TT bar deformation by itself until we get to a certain dimensionless value of the coupling. This theory lives on a cylinder, a flat cylinder of circumference L. So the dimensionless coupling is this lambda divided by L squared. And when that reaches some value, y naught, that we are very precise about, we turn on a deformation that includes this constant. And all along the way, again, following these earlier authors, we can track through what happens to the energy spectrum of the theory. The way we do that is to trade the deformation in the action for a deformation in the interaction Hamiltonian, and also to recognize the two-dimensional stress energy tensor components as energy and pressure and so on. And when you realize that and that the pressure is dE dL, you get a differential equation for the energy levels that has a exact solution. It's a trivial solution with a boundary condition that they agree with the seed CFT theory at the beginning. Okay, so there's, I already said that we want to start from some ADS CFT dual pair where we understand the seed. And indeed, due to work of Hartman and company, we know enough about that from the field theory side to be able to talk about its count of states in the energy regime that we're interested in, where the energy spectrum agrees with the area in Newton units that one obtains on the gravity in the gravity description. So start from one of these ADS CFT dual pairs where we know what we're doing, and where I want to stress the gravity side is really weakly curved, and so it's a theory we're really interested in. Then we do this deformation. I was explaining that there's that differential equation defining what theory it is we're talking about, translates into a differential equation for the energy spectrum as a function of the seed energy spectrum. And the general solution is this very simple square root formula, where we fix the branch of the square root and the integration constants in here, C1 and J, in terms of the matching to the seed theory. And there's another boundary condition that I'll get to shortly. But the point being, this is solvable. So this is where this notion of an integrable deformation enters. The energy spectrum from the seed theory can be tracked through this deformation. And the count of states goes along for the ride. The levels don't cross, and you just keep track of all of them. Okay, so as we do this deformation, the first thing we need is to understand what it means on the gravity side. And this is where Pear's work and other people's work enters, where we first of all determine what notion of stress energy it is that we should compare to on the gravity side. And there's a pre-existing definition of stress energy, which is the Brown-York quasi-local energy, which is what you'd expect. You take a system in gravity with a boundary at which the metric is fixed, but the variation with respect to the metric derivative radially is not fixed, and gives you what's called the extrinsic curvature. So you fix the metric at the boundary, and you vary the bulk on shell action with respect to that, and that spits out a formula for a stress energy tensor, which obeys all the properties that a stress energy tensor should. And it's this stress energy tensor that matches perfectly with the deformed energies calculated by this integrability of the deformation that I described earlier, with an explicit dictionary between the two sets of parameters. So what we can do is do a deformation where we start from ADS CFT, we bring in the boundary, and there are many, many types of deformations we could consider after doing that. The one that we'll be most interested in here is one that is kind of summarized here on the left, where we bring in the boundary to a certain point in the ADS-CFT system, starting from ADS with a black hole in the center of it. And for time reasons, let me just start from there. So bring in the boundary of ADS with a black hole. At some point, the boundary hits the horizon of that black hole. And when you reach the horizon of a black hole, you actually get a metric tensor which is indistinguishable from the near horizon metric of de Sitter space with the same transverse sphere. And so at that point, if you look also at the dressed energy formulas for the system, you find that the square root part of it just goes to 0. You're free to continue the deformation by switching the branch of the square root. And you find a continuous deformation of integrable deformation where you can continue to follow the states, and the energy spectrum is continuous, where you start adding to the deformation not just this TT bar part, this quadratic thing in the stress energy tensor, but you also add a constant to the differential equation. And when you do that, whereas in the ADS case, the deformation energies match the Brown-York energy of a patch of ADS with a black hole, when you continue in the way I just summarized, just picking a different branch of the square root and continuing the trajectory, you find quasi-local gravitational energies that match the solvable deformed energies of this other part of the trajectory. And it's just another version of the same easily solvable integrable deformation, for which the Brown-York energies that you compute on the gravity side are those for de Sitter, and they match the boundary theory's deformed energy spectrum precisely. So in that sense, so these energies depend on the bulk geometry, and in that sense, you get a function's worth of tests of this duality where the boundary theory's notion of energy and the solvable deformation's notion of energy agree on the nose as a function of how far you go in the deformation, which on the gravity side has to do with where you put the cylindrical boundary within the observer patch of the Penrose diagram of de Sitter. Okay, so that might have all sounded a bit complicated, but really in this subject, that's extremely simple. I mean, it's really much easier than many of the things that we must do in modern quantum gravity research. And again, it's a lot of fun because it's a confluence of many threads of research. The integrable deformation researchers were doing their thing for years, quite independently of holography, and the recognition of the relation to the gravity side has led to an ability to formulate the physics of these finite patches, both in terms of the geometry and then also in terms of the microstate count, just because that stays the same along these deformations. So we're just following the system energy level by energy level. And so if we understood the count of states in the original system of ADS with a black hole, that count of states just continues to hold. So in that sense, rather than using supersymmetry arguments to follow a count of states from a known one to a previously unknown one, we use this integrability of the deformation. Okay, so that's the main point. In this energy spectrum formula, one thing that I should have stressed is that, well, first of all, back in the gravity description, I'm sorry, let me go back to that shortly. One thing you notice is that the log of the number of states here is some finite number. And that's very different from a quantum field theory. So what's going on there? Whereas in the original theory that we started from here, we said that we had a CFT, which is a full quantum field theory. It has an infinite number of states. You can go to arbitrarily short distances. And an aspect of this deformation, which is represented which appears in the square root, is that above a certain energy level in the original theory, which appears inside the square root formula that I keep writing, the deformed energies no longer exist. They become formally complex. And so the statement is that the real part of the dressed energy spectrum, this calculable spectrum, agrees on the nose with the predicted entropy. This deformed theory knows to produce a finite spectrum from what started out as an infinite CFT spectrum. Okay, and again, that was something that was considered a oddity of these deformed theories, but I think it's a feature rather than a bug. So all of this kind of stuff strongly motivates understanding these so-called TT bar deformed theories better. And again, there's really beautiful research going on that front, including especially here. This is a summary of what I just said, and I'm happy to explain, discuss more with anybody interested. Let me just say there's a big open question here, which is how to connect this to the way that de Sitter spacetime and inflation and all of that appears beyond the level of this kind of solvable model, which matched features of a three-dimensional universe. And when we think about how de Sitter space works in string theory, there's a much richer set of configurations that are involved in that. In particular, as you go from ADS to de Sitter, the simplest way we know how to do it involves going from a compactification of string theory on a sphere, which gives ADS, to essentially a compactification of string theory on a hyperbolic space with some quantum effects, for example, Casimir effects, and flux in both cases. The point here being that the internal sphere and the internal hyperbolic space are extremely different. So this part of the procedure I described where we go to the horizon and we can't tell the difference between a black hole in ADS and a de Sitter horizon is true of this solvable toy model that I described. But how is that going to work in something like full-fledged string theory where the internal spaces are very different? Well, there's an idea for that, which is that as we reach the horizon, we're also reaching a regime of diverging temperature. And once you're at very high temperature, you must mix among all the configurations consistent with that horizon. So given that topology does change in string theory, as we heard this morning from David, it's quite possible to, I think there's a consistent interpretation of this in which the internal space, in which the fact that we can't tell the difference between the two horizons does extend to the internal space because we mix among the different topologies. But this relies on the existence of these bounded patches in the full-fledged string theory. And that's, to me, a very interesting open question. And we're starting to address it using the various tools that we have for studying the emergence of space-time in string theory and M theory, where we can ask whether or not it's consistent to have, say, an exponential potential, so-called Liouville potential that stops the various degrees of freedom from going beyond a certain boundary. And if such walls exist in the UV theory, then even in the more difficult case of cosmology, I mean, we often say, oh, there's no time-like boundary in cosmology, but I'm not sure we know if that is the case or not. So one of the directions going on is to understand whether or not these walls exist in the full theory, motivated by the fact that these integrable deformations fit beautifully with that notion as far as they go. Okay, so let me, this is the main topic I intended to cover. Here is a brief, although wordy, set of conclusions. I think we maybe don't have time for this, but just to flash the spin-off to industry that I mentioned earlier, which, okay, I haven't really kept track of time. If there's time, I can summarize it and interest. If there's not, I can just stop. 2 minutes, okay. Okay, well, just for fun. So this is actually where my head is mostly lately. So when we think about cosmology, say in this inflationary theory, we're moving in field space down some potential energy landscape. That's something that we also do as part of machine learning and other optimization problems, where the traditional method is some form of gradient descent, where you're trying to get to the bottom of some landscape, and so at a given point, you measure the gradient and you go in the direction of the strongest gradient. Turns out that you don't, so in physics language, that's friction-dominated evolution down a landscape. But it's possible to get the same or even better results by not having any friction at all. So the problem with friction is that it doesn't conserve energy and you lose some of the nice theoretical control that we enjoy in simpler classical physics problems with energy conservation. So basically one can take, as an alternative to gradient descent and all of its various generalizations, one can take a model where energy is strictly conserved, there is no friction, and say the squared speed limit of the model is the loss. And so as you move around that landscape, you fly around unobstructed until you get to the low-lying values of the loss, at which point you slow down for reasons to do with the relativistic speed limit. You can also take just a two-derivative action with mass going inversely with the loss. So this turns out to work, and the energy conservation gives us a level of predictive control over the results based on the conservation of the phase space measure, from which we see that it's indeed dominated by very small values of the loss function. So this is, in that sense, a kind of spin-off of cosmology, because this kind of Born-Infeld dynamics is a version of inflation that has interesting non-Gaussian signatures. And recently it suggested a way of generalizing the optimization step in AI, and also it turns out sampling in a related way, again, in a way that kind of replaces the frictional dynamics with energy conserving dynamics. And so for fun, that's what I wanted to share along the spin-off side. Let me definitely stop there, and I'm happy to take any questions.
You just say a bit more about the physical interpretation of the de Sitter states. So those all to do with the, again, embedding of the boundary. You think of these as boundary modes, or how are you thinking about the Hilbert space in terms of like what it means to be in one state versus another?
So I'm thinking of it, so let's suppose we started in a microcanonical description of the ADS black hole. So I'm just going back to the CFT spectrum, which includes a band of energies, let's say around delta of C/6, in which there's some band of energies that corresponds to a black hole of a certain mass. And those CFT states are what I would call the microstates of that black hole. And I shouldn't draw, like here, there's this picture, the Penrose diagram. For those microstates, I shouldn't draw anything smooth behind the horizon, right? It's just some set of microstates that describe the states associated with the outside of the black hole, meaning the green part I've drawn here is the outside part, and there's a set of microstates which generally don't have a smooth gravity description, but which account for the horizon entropy. Okay, so let's start from that. And now we do the deformation that we know and love, and the theory deforms in a highly non-trivial way, right? A very nonlinear way with the square root. And that deformed theory contains microstates that are the dressed versions of these microstates. And at the same time, that theory energy levels as opposed to matching those of the ADS patches. After we do the lambda 2 part of the deformation, they match the Brown-York energy of the de Sitter patches. And all along the deformation, that band of energies, that band of states, the count of them, and also their energy formula is tractable. Okay, so does that answer
Yeah,
your question?
no, thanks for the clarification. Yeah.
Yeah. So also on the de Sitter side, I really, when I shade the patch, that's the part that's really gravitational. The microstates are some more complicated mess.
Could you go over quickly again what the relationship between the first part of your talk, the deformations for cosmology, and the AI energy conserving
Okay, so
dynamics? It went pretty fast, and
yeah, I'm sorry about that. I know I'm indulging in too many subtopics here, but actually the last topic is more, sorry, it's more related to the first part of the talk about inflationary dynamics. Well, so I can explain the connection. I didn't explain it very well in the talk, so I apologize for that. There's a certain form of, so in inflation, I had drawn, I had mentioned that inflation requires a potential energy to describe accelerated expansion. And for whatever reason, that potential energy needs to change slowly. One way for that to happen is if the potential energy as a function of the inflaton field phi is a very flat function in an appropriate sense. But another way for that to happen is if interactions of the fields, even if the potential is very steep, interactions of the fields can stop it from moving fast. And that's what happens in what's called Dbi inflation, where it's a relativistic type motion on field space where the speed limit, on field space is what stops it from moving down the potential. It's a generalization of that, which, by the way, is therefore a kind of dynamics that is not dominated by Hubble friction. So basically, the analogy here is gradient descent and that kind of optimization, which is the standard method in say machine learning and so on, is analogous to Hubble friction or slow roll inflation. But there's another option, which is this kind of dynamics. And in Dbi inflation, it's not about the Hubble friction at all. It's sub-horizon physics that guarantees the slow evolution of the potential energy. So if we map that over to this context of optimization, it means that we can still descend the landscape, still slow down, toward the bottom where we want to. And by the way, it's a theorem that we cannot get stuck in a high local minimum, unlike gradient descent, where the phase space contracts because of the friction. So what we're getting from that is that we can conserve energy, so have no friction, and yet still slow down, still do the optimization. So, but the connection to cosmology is through this sort of highly interacting kind of inflationary model, which suggested this spin-off to optimization. Thanks for asking.
and can you apply this to glass systems and
Well, that's a
glassy
great question.
dynamics?
Yeah, so it has good results on kind of synthetic test functions that are in that spirit, like the Ackley function, which has lots of local minima. Yeah, it'd be nice to do that. We're applying it to quantum chemistry as well as computational chemistry, as well as kind of bigger machine learning problems and so on. But the whole, it's a general purpose tool, so the hope is to apply it, widely if we can. So yeah, thanks a lot for the question.
Well, thank you.
Thank you very much. I don't think the mic is on. Maybe my mask is on. There you go. Thank you very much. I neglected to mention that it's been the great good fortune of the Baumeick Institute that Professor Silverstein has agreed to serve on the external board of advisors. So Thank you very much for that and
Thank you.
for an excellent talk.
Thank you.
So you can pester her with questions during coffee, which will start now and end at 20 minutes after the hour.
Thank you. Thank you.
People who state it's just another